Good evening to all of you. Myself, Muhammad Ilyas, Faculty of Mechanical Engineering, B.S.Abdur, Crescent Institute of Science and Technology. I welcome all the participants for the session on BMS and health monitoring using AI. For today's session, we'll have our resource person, Dr. S. Paul Sathyan, Technical Director, NL Technologies, Chennai. It is our great pleasure in welcoming Dr. Paul Sathyan to deliver his expert talk on BMS and health monitoring using AI. We welcome you, sir. I feel very happy in introducing our resource person for this session. Dr. Paul S. Sathyan is a distinguished scholar, educator, and technical innovator whose career spans over 15 years in academia and industry. With expertise in electrical engineering, his work bridges theoretical research and practical applications, particularly in the fields of electric and hybrid vehicles, advanced driver assistance systems, and EV charging technologies. Dr. Paul Sathyan has served as a faculty of mechanical engineering at the Karunya Institute of Technology and Sciences, Coimbatore. Presently, Dr. Sathyan holds the position of Technical Director at NL Technologies, Chennai, where he spearheads advancements in model-based systems engineering with a focus on optimizing adaptive cruise control systems. Dr. Sathyan's academic careers have been marked by excellence and dedication. He earned his PhD in electrical engineering during the year 2017. His earlier academic credentials include ME in Power Electronics and Drives and BE in Electrical Electronics Engineering. As a technical director at NL Technologies, he leads a team of engineers and researchers in pioneering developments in automotive systems engineering. Under his leadership, the team has made remarkable progress in enhancing vehicle intelligence and safety through cruise control. His role extends beyond technical leadership to organizational development. Dr. Sathyan has been pivotal in streamlining operational processes and effectively presenting complex technical concepts, promoting collaboration across teams and departments. Dr. Sathyan's professional achievements are recognized by his active membership in esteemed organizations such as Institute of Electrical and Electronics Engineers and the International Association of Engineers. With this introduction, let me hand over the session to our resource person, Dr. Paul Sathyan. Thank you, sir.
Thank you, sir. Good evening, dear faculty members. It's our privilege this evening to share my little knowledge on AI-based BMS development. Before that, I would like to express my heartfelt thanks to Dr. T. Murugesan, the Vice Chancellor of Crescent University, and Dr. N. Raja Hussain, Registrar of the University. I extend my heartfelt thanks to Dr. P.D. Jaykumar for having given me this opportunity to share my expertise in electric vehicle domain. Hope this audience will be a mixed gathering of both from mechanical engineering as well as from electrical domain. Maybe few faculties would have been from AI, data science, and maybe research scholars who will be looking for some research gaps with respect to battery management system or developing some algorithms for battery management system. So this evening, I'll be covering up the challenges more than like what are the technologies available, so that the challenges would greatly benefit the researchers to fine tune and come up with technologies so that the current gap in the electric vehicle domain can be addressed. As you know that probably this is the fourth generation of electric vehicle that the automobile industry is facing. And you know that there were several times industry has attempted to bring electric vehicle. Because of various challenges, they were not able to bring up this electric vehicle into the market as expected. Currently, the main challenge is the battery. Though in India, though we have our own EV technologies, made in India EV technologies, but still having said that India is almost in the third position of vehicle density or vehicle number of vehicles on road. But still, we are struggling a lot to bring in a technology which is cost effective, which is one of the prime requirement of Indian market, as well as have some effective strategies to boost EV technology in India. So today evening, I'll be focusing on most of the challenges which we feel like that needs to be addressed, that will help boost electric vehicle adaptation in India. Though government has set up a lot of initiatives, announced several levels of subsidies, but still this EV market in India is failing. Whereas like if you look at the two-wheeler market, if you look at the three-wheeler market, it's improving, but not up to the expectation. And particularly if you look at the European markets, if you study the amount of EV being sold, maybe year on year it is increasing, but the rate at which it is supposed to be increased, or the rate at which the EV should be adopted, is not happening right now, and it's reducing. That's one thing that has decelerated the adaptation of EV. The main bottleneck what we are facing currently is the battery. As you know that currently, if you anybody who owns a four-wheeler would obviously say that if I fill the tank, I can go up to 500 kilometers, 600 kilometers. What about EV? Yes, of course, the volumetric density is not up to the mark. It's almost 1/12 of the current combustion vehicles. When you compare the EV with current combustion vehicle, it's almost 1/12. So if you have to match the current volumetric density, then of course we have to increase the battery capacity of the vehicle, but that in turn will increase the risk by 12 to 13%. That's again statistics say that 12 to 13% there will be increase in the risk. As of now, we are hearing a lot of information about EV getting burnt on the fly, EV getting burnt when it was being parked. Several issues are rising up. The main thing is that we have to understand still the battery management system has to get matured enough in order to ensure that this EV technology contributes to the reduction of carbon emission. That is the primary objective in which this EV mobility has taken its start. But as of now, the contribution is not up to the mark. The present challenge is the battery technology. If you have a matured BMS, definitely I think if the issues like thermal runaway, if the issues like burning of the batteries are addressed, definitely I think the adaptation of EV will definitely increase. That's the current requirement of EV industry. Moving forward, let me share my presentation with this little overview what I have given you. So as of now, most of you would have come across these terminologies, maybe from the other resource person, maybe from the industry point of view, and what are the challenges that industry is facing, and particularly the EV market is facing in terms of design parameters for the battery packs of lithium-ion battery, right? As you know that electrical requirement is there, right? It should have proper voltage and current capacity. What is the ampere hour capacity of the vehicle battery? What is the overall dimension? Because dimension of the battery is going to play a very major role. What is the energy density? What is the volumetric density that we can think of? Then what is the price? Currently, we know that almost 50 to 60% of the vehicle cost is eaten away by the battery. And currently, the batteries have a decent lifespan of around 5 to 6 years. And after that, again, we have to invest almost 50 to 60%. When you look at that particular aspect, that's one of the bottleneck. So how to extend the life of the battery? That's one of the question mark. Now, if you say that if I have to extend the life of the battery, there was one question when I was interacting with one of the colleague who was thinking of buying an EV. He was asking a question like, if I have to replace the battery, that means like, can't the battery be reused? Maybe you should understand that when we say that the batteries cannot be used in EV after 5 years, that means like it loses its characteristics, it loses its ability to serve in the EV domain, but whereas it can be used as an energy storage device for a solar or a renewable plant. So the factor that is when the battery percentage falls below 80% or battery state of health falls below 80, obviously it loses its ability to serve in a platform which requires high current or high power rating, and the rate of current change is also high. The performance degrades when the state of health goes below 80%. So that's what it means. But still the battery can perform better when it comes to when you reduce the rate of change of current, right? The discharging rate, if that can be reduced, then obviously the battery can perform better. But when it comes to the electric vehicle, nobody wants to lose its performance after 5 years. So that's where we say that the battery goes battery cannot be used after a particular lifespan or after covering certain kilometers of run. So the design parameters, the mechanical aspects, if you say what is the shape of the battery, what is the dimension, and when it comes to the cell construction, right, what is the type of electrolyte binder separator between anode and cathode, what is the current collector that you are going to use, what is the electrolyte that we are going to use, those are the important parameters which actually decides the cost of the battery as well as the manufacturing cost, manufacturing process, the manufacturing. So something has to be done on the manufacturing side, wherein like we can try to improve the components of the battery and still bring down the cost of the production cost, whereas we increase the performance like conductivity, electrochemical potential, so on and so forth. So if you look at the internal and external causes, so the possible causes, the main possible cause a battery can explode or battery can create a problem is collision or shock. Now it is being addressed. As you know that one of the top Indian EV, they have Euro NCAP 5, the topmost ranking that any automobile or any four-wheeler can achieve. That Euro NCAP certification has been obtained for an EV. That shows that that vehicle has good mechanical strength to avoid any malfunction of the battery in the case of collision. That is being addressed. The vibration, the deformation, the metallic lithium plating that is being done. So these are some of the possible causes when you separate it as internal and external, right? Most of the problem occurs internally because of sensor failure. It can be a temperature sensor failure, it can be voltage sensor failure, it can be a current sensor failure. So how these sensors can be mimicked, or something like if there is a sensor failure, how your AI model should behave, can we create a soft sensor by which we can mimic the behavior or correlate, say for example, if the current sensor fails, can we uh, relate with respect to voltage and temperature and try to estimate the current for some movement, not for a continuous or a longer period. For to some movement, can I detect or can I predict the value of current in case of a current sensor failure, or in case of temperature sensor failure, how can I predict the temperature with the other associated parameters like current, voltage, etc. So why can't an AI model can be generated in the case of a sensor failure? That is one of the interesting area where currently industry is trying to move on, so that this type of failures can be addressed with the help of soft sensors, which can be modeled using AI, right? Then in when we look at the internal battery faults, of course we know that overcharging, over discharging, internal short circuit or external short circuit, overheating, accelerated degradation, thermal runaway are some of the major issues with respect to internal battery faults. We'll be addressing some of the internal faults, how it can be considered when we model an AI, right? When we develop an AI model, how these internal battery faults can be incorporated, how it is happening. Maybe in the coming slides, I'd like to share a few of the details so that that can be considered whenever we develop an AI model for a particular battery. When we talk about the topology of BMS, yes, most of you would be aware, like we have a centralized network, we have a modularized distributed network or decentralized network. So these are the three basic architecture I can say that BMS is of. Slowly, these architectures are evolving with the concept of how do I reduce the number of sensors, how do I ensure that with minimal sensors I will be able to get the complete uh, current flow, complete information about the battery, complete or completely monitor the performance of the battery with minimal sensor. What are the architectures that I can follow? So these are some of the concepts are there. So when we talk about the failure mode, 14 failure modes have been identified with respect to BMS. Like the primary concerns that I told you, like it can be an overcharging, over discharging, till one run away. So it can be of these four categories. It can be excessive discharge, poor capacity consistency, battery cell leakage, right? When we particularly work with liquid electrolyte or gel electrolytes, definitely these leakages are uh, most common now. So how we can do that? Uh, when we actually think about like faults, okay, now people are trying to research and drill down and find out an AI model wherein like how we can diagnose or use AI models particularly for fault diagnostic purposes. So if you look at the fault diagnostic algorithms, there are two categories. One is model-based methods and non-model-based methods. So in model-based methods, like they will be using some state estimation methods, parameter estimation, structural analysis, right? Parity space, in state estimation, like Kalman filters, right? Observers, they try to develop a model-based methods in terms of battery characteristics as well as in terms of fault diagnostics, right? So when it comes to a non-model based methods, like we have signal processing, knowledge based, like expert system for CAN, and so many approaches are coming, kept on evolving, but still the gap is there, right? So how to do these things? But primarily, when a BMS is designed with the help of AI models or the present algorithms, few of the challenges what I have posted on the screen is the internal SOC error, right? How do you, since it's a regressive integration, any errors in the initial SOC assumption will definitely lead to a bias. So there will be a bias or an offset that will always be available in our SOC estimation. That means like knowingly or unknowingly we are just inducing an error into the system. So how do I get the initial SOC value, right? So how do I model it? Okay. Most of the AI models try to get the data from online data set or conduct some internal tests in their labs, try to get a data of the battery, right? All those things are done, but how this initial SOC is being considered? Then the current measurement error, particularly in the case of noise, uh, when there is a noise in the signal, how this noise are handled. Then current integration error, particularly when we use Coulomb methods to estimate SOC, how this current integration error is handled. Then uncertainty in the knowledge of battery capacity, when particularly using Coulomb counting methods, it assumes that the assumes perfect knowledge of timing oscillation error, whereas like when it comes to battery capacity, again there is a gap that is being addressed. So if you look at why a BMS fail, right? There are a few things that I told. What are the reasons for the battery failure? Now I'm just showcasing you some of the reasons that has been listed down, which talks about the failure of BMS. It can be a cell imbalance. It can be an overcharging, right? That exceeds the maximum safe level for charging and can cause permanent damage to the BMS, because BMS is designed to a particular voltage level. So when it exceeds, obviously it affects the voltage sensor. When the current exceeds a rated value, of course it affects the uh, current sensor. So undercharging, then temperature related issues. Most of the time, like what we have observed is that like uh, it's just an analogy that I'm giving. Most of the time, the when somebody is doing a research for the battery management, they will study only the thermal aspects, and there will be somebody else who will be studying only about the electrical aspects, and somebody will be studying and doing some research only related to chemistry aspects, whereas the other two parameters are considered as ideal, right? So if you look at these challenges, right, these primary causes of BMS failure, we have to, whenever we model or whenever we develop an AI algorithm for a battery management system, all these things, the chemistry, the electrical aspect, as well as the thermal aspect, all these three are should be brought together, because any chemical change will get reflected in terms of electrical quantity. Any electrical quantity would obviously yield to a mechanical changes, right? When there is an increase in the amount of flow of electron, obviously the current increases. When the current increases, there is an increase in the thermal aspect. So how do you so whenever we do an AI modeling, we have to consider the whole uh, characteristics of lithium ion battery, and these are some of the algorithms that you would have come across so often, which talks about like how these faults can be diagnosed. But I'm not going to dwell and say deeper into these particular algorithms, and I'm not going to benchmark these algorithms. Yes, of course these algorithms are there, but what I would like to recommend the academicians as the researchers is that ensure that when these algorithms that you come across address the three aspects which are required for a battery management system. So when it comes to the package system, when multiple cells are connected together, multiple BMS for each module are integrated together, right? So how it is going to monitor the busbar failure, right? If suppose the main circuit connector of the power supply system fails, how it is being monitored? And the strictness of high voltage contactor. Suppose because of high current, if the contactors get stuck and doesn't open, what will happen? These are some of the potential issues that that is going to affect the performance of BMS. It's not just the failure of battery, it's not just the failure of BMS, it is also the other protective systems that is there in the vehicle. Even if it is going to fail, though the battery is good, though the BMS is good, but still there are lot of chances, like because of the other failures, you are still going to have fire in the vehicle because of thermal runaway or any other issues, whatever it may be, right? Okay, so as I told you, like the physical properties needs to be modeled, the chemical properties and the electrochemical properties, all these three together is going to contribute for the lithium ion batteries performance. So BMS, when you design or when you are considering developing an algorithm for battery management system, all these three things have to be brought together in order to understand, right? Okay, now having understood like the challenges that can occur because of a failure of battery, failure of BMS, and the associated system. Now let's dive deep into this electrolyte concepts, right? Because there are lot of research going on in this electrolyte, keeping the anode cathode mostly common, trying to address the leakage issue, trying to address the puncture issue, trying to address the thermal runaway, right? So how can I eliminate this, or I would rather say that the electrolyte is the more what to say, sensitive area in the battery, which may lead to bursting of the cell. So how do I change this? How do I deal with this? So basically there are liquid electrolyte, solid electrolyte, and solid liquid, that is a gel type electrolytes. Three different types of electrolytes are there, right? So when I talk about electrolyte, it comes into a chemistry aspect. Though it is a chemistry aspect, you should also understand like it is going to contribute for the thermal aspect also. So how much heat that is going to give, or in simple terms, if I have to say, what is the resistance of this electrolyte? Because the resistance is going to give you some amount of heat. Some amount of heat is going to raise the temperature of the cell. Whether that increase in the temperature, whether it is addressed or not, has also to be taken into consideration. So when we talk about like main components of electrolyte, we have like solvent, lithium salts, additives. So all these components inside an electrolyte is going to play a major role, right? So for your understanding, like I have collected some information with regard to different electrolytes, right? Maybe I'll try to compare it to first. Maybe rest of the things I'll leave it for you for your understanding, right? Let's take two different electrolyte, liquid electrolyte and ceramic liquid electrolyte. So okay, let's uh, so when we compare the electrolyte, yes, of course, we need to have the conductivity as the primary comparator, then the thermal stability, what is the mechanical strength, electrode wetting, right? Flexibility, electrochemical stability window. So these are some of the key important what to say, performance index with respect to liquid electrolytes or any electrolytes, right? So if you look at this, ionic conductivity is good for liquid electrolytes, but whereas the thermal stability is very poor. That is the reason why now industry is slowly moving from liquid electrolytes, trying to find an alternate for liquid electrolyte, because thermal stability is very poor. So what is happening is that when we try to just model the electrical parameters alone or the mechanical parameters alone while making an AI model, definitely that AI model will not be able to give you the appropriate result when the temperature exceeds certain level, right? So that is one of the reason why BMS fails, right? So if you move on to maybe the other solid polymer electrolytes, if you see, the ionic conductivity is poor when compared to the liquid electrolyte. If you see the liquid electrolyte, it is having maximum, but when it comes to the solid polymer electrolytes, it is very, very less. So that's where now industry or most of the research institutions are working to find out some kind of chemistry wherein like you get better thermal stability and as well as ionic conductivity. Meanwhile, without compromising the mechanical strength also. So there are important things that needs to be done. So more in most of the institutions and academia collaboration, they do an interdisciplinary research wherein like they try to combine researchers from different domain together to just work on electrolytes. So you can think of a collaborative research wherein like if you are still trying to develop an AI model only considering your VI characteristics or only considering the electrical characteristics, then we may not be able to do justice when the temperature goes beyond a certain level. So electrolyte selection plays a very major role because energy density plays a very major role because battery electrolyte also largely affects the reversibility of the electrode material, right? During charging and discharging, you have charging process happening, discharging process happening. So how this energy reversal is happening. So that electrolyte plays a very major role. Internal resistance, of course, you know that it is the ohmic resistance that may lead, that leads to joule heating, right? And then the rate performance, right? What is the mobility of lithium ions, right? If the mobility of lithium ions is very less, then we cannot expect a quick acceleration behavior which is required for the electric vehicle, right? That is why whenever the capacity of the battery comes below 80%, what does it mean is that the battery has lost that mobility. The rate performance has degraded a lot. So that is one of the key important reason why we need to ensure that we select a proper electrolyte, right? Then for high temperature performance, yes, of course, what are the severity of side reactions at the electrode and electrolyte? So what are the side reactions that is happening? It's more like a chemistry related. I don't want to deep dive into it. Maybe any researchers, if you are interested, definitely I recommend you to go through that particular part. And then the cycle life. Of course, cycle life, everybody would like to increase from 5,000 cycles to 10,000 cycles so that the life of the batteries are extended or the kilometer of run of the battery is extended. So these are some of the key things. Right, when we talk about BMS, of course, we are trying to, we would have come across these common terminologies like SOC, SOH, and RUL. But conventionally, we just go with Coulomb counting method to estimate the SOC. Already I have told you what are the limitations of Coulomb counting, and then the open circuit voltage along with Coulomb counting. Sometimes like we go for advanced methods like Kalman, extended Kalman filter, machine learning model to estimate SOC. Right? When I come across this SOC, when you particularly estimate with Kalman filters the initial values, the initial current values, the initial state of charge, if it is not estimated properly, obviously the charger will try to overcharge the vehicle, overcharge the battery. When the battery is overcharged, obviously it leads to bursting of battery. So in estimation, of course, we need to be very careful how do we select the initial values. Then state of health, is one way of representing the degradation or deterioration of the battery. Then a remaining useful life. A lot of mathematical models are coming up, but mostly considering the AML models, mostly considering the electrical aspects alone, right? Then when you talk about the data types or REL prediction, most of the time we go with the numerical data, uh, what is there. Then for the different types of battery like lithium ion, lithium metal hydride, nickel metal hydride, different battery types, we have a different categorical data, cycle counts. Mostly the data what is available is going to be a time series data. When you have these informations, we start to develop an AI model because we have a data, right? And what we try to say is that when you start developing an AI model, try to understand the from the data that you are, try to understand what is the characteristics of that particular data that you have, whether that lithium ion battery has contributed for a rate of change or the rate percentage which matches with the electric vehicle, which matches with your application. Say for example, if any vehicle wants to accelerate from 0 to 100 within 3 seconds, is going to be higher when another vehicle which wants to accelerate within 10 seconds. So for a 3 seconds, it will be much higher when compared to a 10 seconds. So obviously the characteristics will also change. So whenever we take a data, try to understand, study the behavior and behavior of the current change, try to study the behavior of the temperature, and then analyze it for the application, for which application this particular data has been used. We cannot take a data from the open source, though it is for a lithium ion battery, and try to use it for understanding the charging and the discharging rate of an EV, right? It can be a two-wheeler or it can be a four-wheeler. For two-wheeler, the characteristics is entirely different. For four-wheeler, the characteristics is entirely different. So in this case, when we take a data which is not meant to be used for a particular application, if you are doing it, you are getting a result. Of course, we'll be publishing. Of course, we will be trying to develop some algorithms. But when it is tested on the ground, the algorithm fails. That is the reason why, as an academician, as a researcher, whenever we try to take a data, try to understand it. This is another aspects of AI modeling. The other aspects, whatever I have told you, adding one more layer to it. When you take a data and try to develop an AI/ML model, before doing that, try to analyze the data, try to understand from the characteristics, try to understand, first of all, plot the time series data. That will give you a bigger picture, that will give you a bigger understanding how the rate change has happened, what is the rate in which the current has increased, what is the change in the voltage, what is the change in the temperature. Try to analyze that and then try to figure out for what application this battery would have been tested. Sometimes the data source or the data provider would have given in the website itself, saying that this is for this particular application, maybe for a cell phone, maybe for an two-wheeler. Don't try to take that particular data and fit it into an electric vehicle, right? Particularly for a four-wheeler, right? So this wrong data source being selected for a particular AI model, which is going to sit in a different application, though it is an EV. Two-wheeler is also called as an EV, four-wheeler is also called as an EV, or you can call electric bus as an EV, but they are all not the same, right? If you the people who may be working in electric vehicle domain would be able to understand what I'm trying to convey, right? In that particular aspect, try to understand the data and then move forward in that. right? So when you try to understand the remaining useful life, this is very why we are insisting on remaining useful life, is that like this is the key point which will say that how far, when you are supposed to replace the battery, right? How a tire mechanic looking at the threads in the tire will say like this is the time to replace the tires, or this is the time that you need to rotate your tires. Likewise, this particular key parameter will say that like, okay, this is what the remaining life, you can use it for another 1,000 kilometers, you can use it for another 10,000 kilometers. So for arriving at this remaining useful life, most of the approaches would be like AIML model, then estimation approaches, then analytical approaches. So in all these three, right, it can be a linear or non-linear. It can be a parameter, how this analytical models are considered, what is the scope, what is the initial condition, what is the state estimation techniques being used, what is the interpretability, what is the feature engineering. Try to analyze everything before we use an AA model, or decide, okay, this is the model that I'm going to use, this is the estimation approach that I'm going to use. Right? Try to figure out and try to correlate it with your application. Right? So classification of capacity degradation methods, like there are model based methods, fusion based method. When I talk about fusion based method, it's more than one or two approaches coming together, so that the estimation what we do is more close to the real world data, right? So when we use an AIML model for SOH estimation, yes, SOH estimation, of course, we have a lot of challenges like data acquisition, uh, what is the error, what is the accessibility in the error, what is the interpretation, how can I interpret on the result. All those things, challenges are still there, right? And in general, most of the problem that we are facing is that what is the standard, right? When I say this is the SOH, this is the RUL, what is the benchmarking value that I can use to compare it, right? The researchers would know, the doctorates would know, like whenever we do a research, we try to benchmark our findings, compare it, and say that this is this percentage better, right? What is benchmarking? That still there is a lack of standard. It's all because like the data that we take from the open source in most of the researchers are not matching the application for which that particular battery has been tested, right? The results whatever available is not matching the application what is being tested in the real world, right? That's what then the improper selection of functions, data scarcity. Now most of the time we say that data scarcity is there, right? That's where researchers started developing or modeling battery cells. Like lot of research papers are coming up which talks about modeling a lithium ion battery, modeling a battery internal characteristics, so that they'll be able to generate the data which is more close to that, right? So in such case, that we call it as a synthetic data. So when you generate a synthetic data with different tools, like try to generate data which can be more closer to the real world data, right? Say for example, you have a battery cell data which is available. You have a particular specification, say for example 3.7 volt, some 1000 milliampere hour, some specification is available. You have taken the data set, right? Now you are trying to build a mathematical model for it. Okay, you have built it. Now try to test your model with the data available, try to correlate it and find out what is the deviation. If the deviation is less than 2%, yes, of course, you have built a better model. Now use that model to generate data for your application. Don't use the data which was available earlier. Now use the data to generate. Now what you can say that a particular specification of battery cell that you have taken, which matches the behavior data which is available in the net. Once after benchmarking your model, now try to generate a data which can match your application. So it's a what to say reverse engineering application, that approach that you put on that battery cell data which is available, modifying it for your requirement, and then use the data for developing your AML model. That's one thing to address this data scarcity, right? Then as I told you, like you need to do a deep dive study on the battery chemistry also whenever we do the modeling, right? Try to figure out like what is the molar mass, what is the go deeper into it when you try to model it, right? Then have some filtering options to eliminate the noises. Most of the time when you take the data, synthetic data, try to infuse noise signal into it and then try to use it, because in the real world, when you use a current sensor to take out the current signal from a cell, it is going to have huge level of noise. Try to address that particular aspect, right? So maybe I'll take another 10 minutes to address this solid state batteries, which is now coming up, which is also predicted to have the same kind of challenges what liquid lithium ion battery has faced. Maybe for those who are interested, right, you can have your research on this particular platform like solid state batteries, right? So these are some of the, okay, let's compare a solid state battery with a liquid electrolyte batteries, right? So the key objective of having a solid state battery is that to remove the liquid electrolyte, which reduces the risk of fire as well as reduces the risk of thermal runaway. That's the primary thing. When it comes to the energy density, now currently it is around 160 to 250 watt-hour per kg for liquid electrolyte. Now we are trying to improve it to 300 to 800 kilowatt hour per kg, so that the range is extended for the same weight on the vehicle, because the weight will add to the add as a load to the vehicle. So obviously the power which is consumed for moving the vehicle on top of the power which is required to move the dead weight of the vehicle also. Then the lifespan, like solid electrolyte battery, longer lifespan due to reduced degradation. The degradation effect is much lower when compared to the liquid electrolyte. So you can have an AI model which can also bring in this degradation effect also. Like then comes the charging speed. So you can go up to ultra fast charging, that is 80% in minutes. That is where industry tries to benchmark. Most of the leading universities which are doing research in batteries, they are trying to benchmark this requirement. Then temperature stability. I have given you a comparison how this temperature stability is poor when it comes to the gel type and other type, right? How we can improve on that particular thermal stability, right? Maybe from a mechanical background, you can work with chemistry department to develop a electrolytes which is having high conductivity, meanwhile without compromising the thermal stability also. Then dendrite suppression, maybe I'll try to give little more information on the dendrite which happens in the solid state, how it can be potentially modeled and how it can be addressed. So solid state, to give you a brief idea about solid state lithium ion battery, yes, as I told you, it has very fast charging speeds, reaching around 80% of the capacity in minutes, high temperature stability. It has a compact footprint, like when electrolytes are eliminated, the need for liquid contact, and potentially allowing automotive manufacturers to implement more lightweight designs with smaller batteries. That's, of course, one of the advantage when it comes to the application point of view, and then improved safety. Few of the examples of solid electrolytes is lithium phosphorus oxynitrate, polymer electrolytes, so on and so forth. So to give you a visual impression of how solid state battery and liquid electrolyte battery works, is that you have a separator in between anode and cathode, which is removed in solid state batteries, wherein like charges can flow freely. The property should be, it should have high mechanical stability, dendrite formation should be addressed, thermal stability should be there, chemical stability should be there, and electrochemical stability. So bringing all these properties, or trying to achieve all these properties in solid state battery, is the key thing. And then to add few more things is that, like, we try to increase the life cycle of the battery. Presently, what they say is that it is somewhere close to 1500 cycles, and make it even twice, right? 2 to 10 times higher than lithium ion batteries. That's the scale in which they are trying to go. But the present challenge in lithium ion battery, solid state lithium ion battery, is that, like, the manufacturing complexity is yet to be addressed, right? Still under development phase, but whereas lithium ion battery, it has matured enough. When it comes to the cost, because still the development is going on, still we have not arrived at a solid manufacturing process and the technology, still the cost is a little higher, on the higher side. It can be, it is almost similar to that of an LED. LED bulbs was little on the higher side, maybe 5 to 8 years before, but when you compare it now, the price has come down because LED technology has got to into a maturity level, higher maturity level, and the commercial, currently it is not commercially available. Very limited people are doing some research, right? So solid state batteries is still there. Maybe okay. So the common failure mechanism originate with lithium dendrites, right? So you can see the cracks which are formed inside the cell structure, right? You have cracks there, and because of this cracks, right, the mechanical strength comes down, the electrical conductivity comes down, and that's where the battery starts to fail, right? Deformation happens, lot of deformation happens, bulging of batteries. So these are some of the uh, challenges that are presently there, right? So these are some of the challenges that I have posted, so that rather than telling you what are the AI techniques that are available, I am trying to give you a direction in such a way that you develop an AI model considering all these things, because at the end of the day, if the AI model doesn't consider all these things, or if you don't build a AI model considering all these things, still, even if it is going to be a solid state battery or any electrolyte battery, still it is going to fail. So currently, if you have to address, building an AI model is important, but when you build an AI model, build it in a holistic approach. Maybe with a one case study, maybe I would like to end my session. This is a case study that has been published. I may not be able to say which brand it is, right? So it happened in 2019. One of the leading car manufacturer, electric vehicle, leading car manufacturer. In 2009, what I'm going to share is a real case study because of the failure of BMS algorithm, right? The company lost its market share by 30 to 35%. This is a real case study because of a BMS failure, right? So what was the issue is that like in 2009, one of the leading, now they have resolved it, but they have lost the market by 35%. It's all because of BMS failure, not because of anything else. The other technology, motor drive technology, the power electronic components, the vehicle design, the aesthetics are, you can say it's an wow feature. But when it comes to BMS, a small component, but it is supposed to be the heart of the vehicle that failed, that brought down their market share by 35%. Even now, you would be seeing a lot of two-wheelers are facing such kind of issues. So this is a real case study, which the company started working on it. They made their technology matured enough to a certain level. Now, even if you ask like whether they have achieved 100%, still not. But they have improved almost 30-35% more than what it was in 2019. They are continuously researching, they are continuously trying to find where the gap is. And whatever gaps that I have posted, it is from that case study. So that as an academician, as a researcher, let's not fail in the same area what others have already failed. Let's learn from their failure so that we can win at the earliest. That's the concept that I would like to share. But in 2019, let me quickly run through that case study. The range which was expected by that particular vehicle fall by 41%. Say, for example, if they have estimated a range of around 100 kilometers, just a numerical assumption, the actual test result showed 60 kilometers only. Then they found out like the model that they have built, they haven't given a space, or they haven't considered the battery's temperature range, which is supposed to be considered. If you ask me what is the margin that they have missed their model by a margin of 6 degrees Celsius. A matter of 6 degrees Celsius, they failed to integrate it into their model, AML model, because of which they faced a lot of challenges, but now they have improved a lot. This is one particular case study when the temperature was not considered. Then what they did, they started bringing in the battery chemistry into their BMS model, try to develop an AML model. Now, if you ask me what technology they are using, is that I can say that they are using an AML model, but their AML model try to bring a whole picture. They are not trying to take only few data which is available. They tried their best to replicate the chemistry property, mechanical property, the operational behavior, everything, the ambient temperature, everything they brought into picture, wherein like they brought in all these components together, whatever I have shared for the case of lithium-ion batteries with liquid electrolyte. They modified their BMS algorithm, and that's where they were able to improve their performance, and because of which now they are almost like in the top 5 places in the EV market. So that's about BMS, and that's about how we should model a BMS, particularly when we consider an AI/ML model, right? So that's from my side. Maybe any questions that you would like to ask, please feel free to ask.
Once again, good evening to all the participants. On behalf of the organizing committee, I would like to express my sincere thanks to Dr. Paul Sathiyam for his expert lecture on BMS and health monitoring using AI. Our resource person shared various aspects on developing algorithms for BMS. He also gave insights on important aspects such as BMS design challenges, causes of BMS failure, including electrolyte selections, and also he touched upon solid state battery technology. We hope this session is very informative and useful for everyone. I would like to thank all of you for attending this program. Once again, I thank you all for being with us. Thank you, sir.
Thank you, sir.